Welcome to an elementary synthetic geometry-based introduction to inversion of the real plane with respect to a circle course, episode 6, lecture 6, in which we will cover our next 9 theorems, numbered 15 through 23 in the following manner. First, we will look at the theorems number 15, 16, 17, 18, and 19, which are the converses of the theorems number 10 through 14, which we proved in the previous lecture. In particular, the theorem number 15 is the converse of the theorem number 10. The theorem number 16 is the converse of the theorem number 11. The theorem number 17 is the converse of the theorem number 12. The theorem number 18 is the converse of the theorem number 13. And the theorem number 19 is the converse of the theorem number 14. During the discussion of these 5 theorems, I will present a template which can be used in order to generate the proofs of all 5 theorems, and together we will look in great detail at a proof of the theorem number 15 that precisely uses that template, and the proofs of the remaining theorems, numbered 16, 17, 18, and 19, should really be generated by our viewers on their own using precisely that template, over which we will go in great detail when we will discuss a proof of the theorem number 15. Next, we will look at 2 theorems, number 20 and 21, which will study how inversion of the real plane with respect to a circle acts on circles that are concentric with the circle of inversion. Next, in the theorem number 22, we will prove the so-called fundamental theorem of inversive geometry. In some texts, some authors refer to that theorem as main lemma because the material of that lemma is used and reused throughout the study of inversive geometry. That is why it only makes sense to refer to it as the fundamental theorem of inversive geometry, and that is why we will bestow a special name on that theorem. We will refer to it as ICSTT, or I for inversion of the real plane, C for with respect to a circle, S for similar, T for triangles, and T theorem. Inversion of the real plane with respect to a circle, similar, triangles, theorem. At the end of the proof of this theorem, we will understand why, as a mapping of the real plane onto itself, inversion is an anti-conformal mapping. We'll understand how and why does this phenomenon come about. Next, we will look at 2 very straightforward corollaries of the theorem number 22, and in the final part of this lecture, we will prove the theorem number 23, which studies how inversion of the real plane with respect to a circle acts on circles that do not pass through the center of inversion, but which still have 2 distinct points in common with the circle of inversion. Then we will look at the Euclidean tools only construction of the images of such circles, or an algorithm that can be used in order to construct the image of a given circle using the compass and a straight edge alone. Finally, we will look at another curious corollary of both the theorem number 22 and the theorem number 23, according to which the center of inversion of 2 circles, which are the inversive images of each other, doubles up as a center of homothety of the parent plane with a certain coefficient. According to the theorem number 15, under the inversion of a plane with respect to a circle with positive power, shown with the plus sign here, plus r squared, under the inversion with positive power, any circle, such as the circle Q shown over here in green, that passes through the center of inversion and has precisely two distinct points in common with the circle of inversion, see, such as this point over here and this point over here, is taken into a straight line, L, that passes precisely through the two given distinct common points between the given circle Q, shown in green, and the circle of inversion C, shown in white. Before you try to generate a proof of the theorem number 15 on your own, you may want to spend a little bit of time observing the following animation that I put together for you using the free software called GeoGebra. In the animation that you saw a few seconds ago, the red image of the runner point that was blue and that traversed the given circle Q that passes through the center of inversion and has precisely two distinct points in common with the circle of inversion was what? Was precisely a red line that passed precisely through these two points in common between the given circle and the circle of inversion. And how can we prove that visual observation, or how can we explain this animation experiment? Well, this theorem, the theorem number 15, and all the other remaining four theorems, 16, 17, 18, and 19, are proved in essentially or fundamentally one and the same way, following the following template that I outlined on the right side of the board. And that template amounts to the execution of basically the following four steps. First, we construct the line of centers. What is the line of centers? The line of centers is a unique straight line that passes through two distinct centers of two distinct circles. And in our case, this is precisely what we have. We're given in the premise of the theorem number 15, we're given the circle of inversion C, shown in white over here. And what does that mean? That means that in the absence of other constraints, we are given the location of the center of that circle, the point O, and we're given the length of the radius of this circle, technically a strictly positive real number. We're also given the circle Q, which means we're given the location of the center of that circle. The point Q is shown over here in green, and we're given technically the length of the radius of that circle, and that radius is yet another positive real number that is calibrated against the other real number, the lowercase r, in such a way that the two circles at hand intersect, and that means they have precisely two distinct points in common. The point that's on our right, let's say, named F1, and the point on our left named F2. As such, in all these theorems, we are given two distinct points: the center of inversion O, the center of the circle of inversion, and the center of the given circle, Q. Two distinct points define a unique straight line, and that is precisely the unique straight line that we construct in the first step, the straight line of centers. I name it lowercase p, you can name it anything you want. The straight line that passes through the centers of two circles, or otherwise known as the line of centers. That line of centers will intersect the given circle Q at two distinct points, the center of inversion, O, and another point. Name that point anything you like. I named it uppercase P. This is the algebra. This is the geometry of this situation. The straight line of centers intersects the given circle Q, shown in green, at two distinct points. The center of inversion, we're not interested in that point right now, and its diametrically opposite image relative to the given circle Q, the point uppercase P. This is the point that we're interested in. As the second step, we reflect that point with the given power with respect to the given circle into its image point. In this particular case, this point P is located strictly outside of the circle of inversion C. We know that according to the appropriate theorem that we proved earlier, that point P will be taken into the circle of inversion C. It will be located somewhere inside. I named that point P prime, and this is what precisely we do in the second step. Reflect the point uppercase P obtained in the previous step with the given power. In this case, this power is positive. In yet another case, the power will be negative. It doesn't really matter. We reflect this point in the given circle with the given power into its image point P prime, and then we pick a point, let's say the point A, that is distinct from the point P that we picked over here. And we do the same thing to the point A, our sample point that represents the runner point, the blue runner point that you saw in the animation a few seconds ago. And that point is distinct from the point P, and we reflect that point with the given power. With the given power, this time the power is positive. In the other case, it could be negative. So we will reflect the point A with negative power. In this case, we reflect that point with positive power. And again, let's say in this case, this point happens to sit outside of the circle of inversion by the corresponding theorem. It will be thrown inside of the circle of inversion. This will be the point A prime. So in two steps, templatized steps that you will play out on your own by yourself when you will be generating the proofs of the remaining four theorems, we have our point P, its image with the appropriate power, the point A distinct from P, and its image A prime under the appropriate or given power. What do we do next? That's step number three. We form a triangle that connects our two original points, P and A. In this case, it will be the triangle OAP. So we pick our triangle in such a way that the center of inversion of the triangle is always a vertex of this triangle. And in this case, this triangle will have which property? In this case, this triangle will be right with the magnitude of the interior angle at A precisely equal to 90 degrees or pi over 2 radians. Because by construction, this is a circumference angle that subtends a diameter of a circle by the corresponding theorem, the Thales' theorem, let's say, the magnitude of the angle OAP is right. Now we still work with the center of inversion, but now we take our images, the points P prime and A prime, the ones that we obtained in the previous step. We take these 2 points, the center of inversion, and we form yet another triangle. And for example, this triangle will be OP prime A prime. And the question is, what interesting property must this triangle possess under the premise of the current theorem? Well, this is the fourth and pretty much the final step in this template, because always, always, always we will have the following workhorse formula that holds true. Condition 3, definition 1, this is how we defined the geometric transformation that we're studying right now, the inversion of the real plane with respect to a circle. For the original point A and its image A prime, the product of the distances of these points from the center of inversion must be equal to the square of the radius of inversion of the circle of inversion. And exactly the same relation must hold for the pair of points P and P prime. The product of the distances from the center of inversion to the point P and then P prime must also be one and the same square or one and the same radius of inversion. Now we drop the square of this real number. The expression shown over here on the left hand side of the equal sign must be equal to the expression shown over here on the right hand side of the equal sign. And now we carve up these two factors, the two factor products, these two products, in a way that is advantageous to us. For example, in this case, we move the distance from the center of inversion to the point P from the right hand side to the left hand side in the denominator, and we grab this distance from the center of inversion to the image point A prime, and we move it into the denominator on the right hand side. We construct this proportion over here, shown here and here. And what else do we observe? Well, by the way we constructed our triangles, in different situations the juxtaposition of the points may be different, but essentially you will always have one angle, alpha, that will be, in this case, when the power of inversion is positive, this angle will be technically shared. This angle will be shared, alpha. You see this angle alpha, this is angle alpha. It will be shared. When the power of inversion will be negative, you will see that this straight line over here will flip to the other side, but the angles will be what? They will be vertical. So the magnitude of that angle will still be one and the same. And from that proportion and the fact that these two triangles, the triangle OAP and the triangle OP prime, A prime, share the interior angle at the vertex A, this angle, to which I refer as alpha, shared. What conclusion will we draw? Well, we'll have no choice but to draw only one conclusion, that based on the side angle side, in modern terminology in Euclid's Elements in book 6, I think it is proposition 6, it will state that when the lengths of the sides in two triangles about one and the same angle are in the same proportion, then these triangles are similar, and that means that the triangle OP prime A prime is similar to triangle OAP. But our triangle OAP is right. By construction, this is how this triangle came into existence, and by the corresponding theorem in Euclid's Elements from book 6, it's the early proposition number 5, if I'm not mistaken. This proposition says that in similar triangles against same magnitude angles lie correspondingly proportional sides. And we go back to our original triangle OAP, and what do we say? Well, the side OP, the side OP in the triangle OAP corresponds to which side? Corresponds to the side OA prime in the triangle OP prime A prime. And in the larger triangle OAP, the side OP lies opposite which angle? Lies opposite the right angle. And that means by the corresponding theorem, the side OA prime will have no choice but to lie against what? Against an angle whose magnitude must be 90 degrees or pi over 2 radians. Consequently, the angle P prime A prime, the magnitude of the angle O P prime A prime must be pi over 2 radians or 90 degrees. And this essentially completes the proof and the claim, this theorem. Why is that? Well, the orbit of the image points A prime of the point A that roams this given circle Q that passes through the center of inversion and has precisely two distinct points with the circle of inversion C must be such that the straight line that passes through the points A prime, that point whose locus we're trying to discover, and the point P prime, must be, that straight line must be perpendicular to the line of centers. But the point A at some point will bump right into the point P, in which case its image will coincide with the point P prime, and our runner point A, or sample randomly chosen point A that is distinct from P, will approach either common point from either side, from outside of the circle of inversion or from the inside of the circle of inversion, regardless, either one, this point or this point, running into it this way or this way. What interesting things will happen in these 2 points? Well, in the theorem number 1, the first theorem of this course, we already proved that under the inversion of the plane with positive power, each and every point that belongs to the circle of inversion is what? Is taken into itself, or we now know the official name, such a point is fixed. That means that at some point the image point A prime will bump into the point F1, the first common point between the given circle Q and the circle of inversion, and it will also bump into the second such common point, to which we refer as F2, and that precisely means that the orbit or the path of the image points A prime must plow precisely through these 2 points, and in such a way that from these points, if you will, the line of centers P must be seen precisely what? Under the right angle, as we proved. And that conclusion precisely means that the locus or the set of the image points A prime is the straight line L, shown in red, that must pass through the 2 distinct and common points between the given circle Q that passes through the center of inversion and the circle of inversion C. And that is how you will reason in the remaining 4 theorems. We will look at the statements of these theorems and I will say a few words, but I will not deep dive into the details of each such proof, because all these proofs essentially are slightly modified or slightly adjusted template that is shown on the right hand side on the board on your screen. Again, one more time, in a succinct way: straight line of centers, point P, reflect with the needed power, any randomly chosen point A distinct from P on a given circle, whatever it is, also reflected with the given power, 2 triangles, one is right, workhorse relation, proportion, shared angles or vertical angles when the power inversion will be negative. The triangles must be similar, the triangle must be right, the corresponding angle must be right, and that will basically lead you to the conclusion that needs to be derived. And the final remark that I will make here is that using the Euclidean tools alone, a straight edge and a compass, the construction of the image of this type of circles is more than straightforward. It actually amounts to 1 step. The points that are common between the given point Q that passes through the center of inversion and the circle of inversion C, they're given to us. All we have to do is take our favorite straight edge, here is my incredible simulation, and snap a straight line that passes precisely through these 2 points, and voila, the straight line L, shown in red over here, is the image of the given circle under the given positive power. According to the theorem number 16, which is the converse of the theorem number 11, under an inversion of a plane with negative power, this time we pay attention because the power is negative, as shown with the red minus sign in front of the square of the radius inversion, any circle Q, shown over here in green, that passes through the center of inversion, the point O, and has precisely two distinct points in common with the given circle of inversion, C, shown in white over here, and we can name these points, for example, as F1 and F2, is taken into a straight line L that passes not through the common points F1 and F2, but which passes through the points that are the diametrically opposite images of the common points, and we can name these points F prime 1, which is the diametrically opposite image of the first common point F1, and the point F prime 2, this point right here, which is the diametrically opposite image of the second point F2 that is common to the given circle Q, shown in green, and the given circle of inversion C, shown in white. Once you comprehend the statement of this theorem, we recommend that you try to prove it on your own using the template that we just explained in the previous segment. And before you do that, you may want to spend a little bit of time looking at the animation that I put together for you using the free software called GeoGebra. And in the upcoming animation, you will see a runner point, a blue runner point that will traverse a given circle Q that passes precisely through the center of inversion, and that point will be blue, and you will also see the red images of that point. And again, try to figure out why the shape of these red images is what it is on your own. Here are a couple of suggestions on how to go about generating a proof of the theorem number 16. On the one hand, it is always possible to take the theorem number 8, in which we prove that an inversion of a plane with negative power is always equivalent to the inversion of the same plane in the same circle with the same center and radius of inversion, but with positive power, followed by a rotation of the parent plane about the center of inversion by pi radians in either direction. And such, it is entirely possible to take the theorem number 15 that we just proved, plop on top of that theorem the theorem number 8, and then claim that the theorem number 16 is already proved. That way, we simply take the result of the theorem number 15 and rotate the parent plane about the center of inversion by pi radians and obtain the image of the given circle under the inversion with negative power that is shown on the left hand side of your screen in red, the straight line L that passes through two diametrically opposite images of the points that are common to both the given circle Q, shown in green, and the circle of inversion C, shown in white. But on the other hand, I still recommend that just about the only way to develop a decent understanding of what is going on with this or that material in any corner of mathematics is to initially at least try to generate as many proofs of all these theorems as you can master. Practice writing these proofs by yourself and on your own. And here it is possible to construct a handmade or custom-made bespoke proof of this theorem based on the template that we explained in the previous segment, and I will go over that template only as a few highlights. Still, we take our center of inversion, the center of the given circle, snap a straight line, P according to the first step in our template. That straight line will intersect the circle that is given to us Q at two distinct points. We grab the second one, this is the point named P. We reflect it in the given circle of inversion C with negative power, this time into the point P prime. Then we grab another point, the runner, at random, that is distinct from P, the point on the given circle Q. We reflect that point with the given power into the point A prime. All the straight lines of interest pass precisely through the center of inversion, all over here. We construct our interesting two triangles, the triangle OAP and the triangle OP prime A prime. We argue that the angles, the interior angles in these two triangles at the vertex O, by being virtue of vertical, they are equal one another. The triangle OAP is right by construction because it is an angle, a circumference angle in a semi-circle. We write down the expressions for the main workhorse formula for our geometric transformation, the inversion of the plane in a given circle. Construct the appropriate proportion, argue that the angles this time are not shared but are vertical nonetheless. The lengths of sides about equally magnitude, if you will, angles is in the same proportion. The triangles must be similar. In similar triangles against opposite equal angles lie correspondingly proportionate sides, and as such we argue that the angle, the interior angle of the triangle OP prime A prime or at the that vertex must be right, and that means that the only possible trajectory for the image points A prime is again a straight line. The argument here is the same as the runner point. A approaches either the first or the second distinct point that is in common with the circle of inversion. We already proved, that was theorem number 2, that any such point is taken into where? Into a point that is diametrically opposite to it. So the point F1 will be taken into its diametrically opposite image F prime 1, and the second distinct point F2 will be taken into its diametrically opposite image F prime 2. F prime 1, F prime 2, and game over. Our image must pass through these points, and through the points P prime. Thus, the only conclusion that we draw is that the image of the given circle under the inversion with negative power is precisely the straight line shown in red L that passes through the points that are the diametrically opposite images of the points that are distinct and common to both the given circle Q, shown in green, that passes through the center of inversion, and the circle of inversion C, shown in white. And once we understand how the proof of this theorem works, we also understand how to construct the image of this type of circles under negative power using the Euclidean tools alone, a compass and a straight edge. We basically snap two straight lines through the center of inversion both times first time through the first point in common, second time through the second point in common. These two straight lines will intersect the circle of inversion at 2 points. The second such points will be exactly what we need, the diametrically opposite images of the points that are in common between the given circle Q and the center of inversion C. And as a final step, we snap a straight line L through these diametrically opposite images, the point F prime 1 and the point F prime 2. The straight line L thus constructed is the image sought after. Again, a proof of the statement will be left to the viewer as an exercise, but here you will argue again in that proof precisely from the fact that you already have a straight line L and your angle at the point P prime will be precisely right. This relationship will be given to you. This relationship will be given to you. This piece right here, the distances from the center of inversion to the point P and P prime. And again, because the angles are here are vertical, these angles are both right. So by angle, 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 the triangles must be what? Similar. And from that, you will deduce that the product of these two lengths must be equal, be in this proportion, and then you unwind it the other way and precisely arrive to that, which will show you that any point A prime is precisely the image of the point A on the given circle when the power of inversion is negative. According to the theorem number 17, under an inversion of a plane with positive power, now we're switching gears and carefully note that the power of inversion is positive. Any circle such as Q that passes precisely through the center of inversion and has precisely one point in common with the circle of inversion C, this point shown over here geometrically, is taken into a straight line L, shown in red over here, that passes precisely through that point, single point that is common to both circles, the green circle Q that passes through the center of inversion and the circle of inversion shown in white C, and that is tangent to the circle of inversion C and evidently tangent to the original circle Q itself. Once you comprehend the statement of this theorem, try to generate a proof of that theorem on your own. And before you do that, you may want to spend a little bit of time watching at an animation that I put together for you using the free software called GeoGebra, and that animation precisely depicts what is happening in the theorem number 17. Don't forget the power of inversion in this case is positive. As a guide through a possible proof of the theorem number 17, we follow the same template that is outlined on the right hand side of your screen. This time, don't forget that I put the negative sign in front of the square of the radius of inversion to reflect the fact that depending on the situation, we will be reflecting our points with either positive or negative power, as the case may be. In this theorem, the power of inversion is positive, but we follow exactly the same steps. We snap a straight line of centers through the center of inversion and the center of the given circle Q. That straight line will intersect the given circle Q at two distinct points, as shown on the upper right hand side over here. Then we will see that this time the second point of intersection, aside from the center of inversion, will be precisely the single point that is in common to both the given circle Q that passes through the center of inversion and the circle of inversion shown in white. See over here, that point is called the point of tangency. We will name it appropriately with an uppercase T. So in this case, our point P and P prime will become T and T again, because why? Because by theorem 1, any point on the circle of inversion, which the point of tangency T certainly is, under positive power of inversion, remains what? Fixed. The official term is fixed or stationary. It's not taken anywhere. And as such, the distance OP and OP prime both times is what? OT, which is precisely R. We grab another point A at random on the circle Q, distinct from the point T, reflected with the positive power, construct two triangles, and so on. Use the workhorse formula. And what do we discover? We discover that the triangle, this time OTA prime, instead of P prime, we will have T will be one and the same point. The triangle OTA prime must be right, and that means that the only orbit for the images A prime of the given points A that roam the circle Q must be a straight line that passes precisely through the point of tangency between the given circle Q that passes through the center of inversion and the circle of inversion shown in white C, and that straight line must be again perpendicular to the line of centers P. Game over, and this will conclude the proof. And as an algorithm for Euclidean tools only, a compass and a straight edge construction. Again, this is very, very straightforward. Snap the straight line of centers, connect the points O and the points Q with a straight line. The point T on that straight line is given to us. Draw a straight line which is perpendicular to the straight line P and passes through the point on that straight line. That can be accomplished, that task can be accomplished in 3 steps using a compass and a straight edge, and thus we will construct the shown in red straight line L that is perpendicular or tangent to the given circle of inversion C shown in white and passes through the single common point between these two circles, or the point of tangency. According to the theorem number 18, under an inversion of a plane with negative power, here again we switch gears and work with the inversion that has negative power, shown with the red minus sign with negative power. Any circle Q that passes through the center of inversion O and has precisely one point in common with the given circle of inversion shown in white over here, we name that circle C. Such a circle is taken into a straight line L that passes through a point that is diametrically opposite to the tangency point T between the circle Q and the circle of inversion C, and that straight line is tangent to the circle of inversion C at that diametrically opposite image point T prime. that is shown over here, the straight line L, the image of the given circle Q, when the power of inversion is negative, is tangent to the circle of inversion at the point T prime, where T prime is the diametrically opposite image of the sole point that is common to both the given circle Q that passes through the center of inversion and the circle of inversion itself. Once you comprehend the statement of the theorem number 18, we recommend that you try to generate a proof of that theorem on your own using the template shown on the right hand side of your screen. And before you do that, you may want to watch an animation that I put together for you using the free software called GeoGebra. In case any of our viewers are in need of a guidance of how to apply the template that we explained in the previous segment to a possible proof of the theorem number 18, where the power of inversion is, again, we're careful to remember, is negative, we follow the same standard steps. So we snap a straight line of centers. We construct a straight line that passes through the center of the given circle, lowercase q, uppercase q, and the center of inversion. That straight line shown on the left in red. That straight line of centers will intersect the circle of inversion and two distinct and diametrically opposite points. The sole point that is in common to both circles, the circle Q that passes through the center of inversion and the circle of inversion, and the point that is diametrically opposite to it, T prime, the tangency point and its diametrically opposite image. Then we grab any point that is random on the given circle Q, distinct from T. Here the role of the point P is played by the tangency point T. We construct the relevant triangles. The angles over here will be vertical, hence they are right. The magnitude of the angle, interior angle of the triangle OTA will be what, 90 degrees or pi over 2 radians, a circumference angle that subtends a diameter. So this triangle here, OAT, is right. We use our workhorse formula, condition 3. Definition 1, instead of the point P, we will have the points OT and OT prime, but both time the distances OT and OT prime are what? Both times these distances are precisely R and R. Again, the radius, so there we go. We construct from this relationship, we construct our ratio. We prove that the corresponding triangles must be similar. This time the angle alpha is not shared, but these angles are vertical. Let's say we'll designate them with alpha anyway, like so. And we prove that the triangle OT prime A prime, OT prime A prime must be right. The triangles in question must be similar, and voila, we thus conclude that the only possible orbit for the image points A prime are such a set of points in the parent plane, which, when connected with the diametrically opposite point T prime, form a right angle with the line of centers, and that precisely would mean that the straight line L thus constructed is tangent to the given circle of inversion C at the point T prime. Again, the power of inversion is negative, and once we understand that proof, the Euclidean tools only construction of the image straight line L of the given circle q when the power of inversion is negative is very straightforward. Snap a straight line of centers. That straight line will intersect the given circle of inversion at 2 points. The tangency point, the sole point that is common to two circles, the given circle q and the circle of inversion, and its diametrically opposite image t prime. That's it, game over. Construct a straight line that is perpendicular to the straight line of centers O, Q precisely at the point T prime. That can be done in 3 steps using the Euclidean tools alone, and voila, game over. The image, the straight line L shown in red over here, of the circle Q when the power of inversion is negative, is thus constructed. According to the theorem number 19, which is the converse of the theorem number 14, under an inversion of a plane with, this time, positive or negative power, any circle Q that passes through the center of inversion and otherwise has precisely 0 points in common with the chosen circle of inversion is taken into a straight line that also has precisely 0 points in common with the chosen circle of inversion. For example, as a pictorial guide of the theorem number 19, on the left-hand side of your screen, we show the circle of inversion named C in white. This is the circle of inversion. We're also given its center, the point O, which is also the center of inversion, and the circle that passes through the center of inversion and has precisely 0 points in common with the circle of inversion. Q is shown in green on the bottom. We're also given the location of the center of that circle, the point Q, designated with the uppercase Q. And the only difference in the outcomes of the theorem number 19 across positive and negative powers of inversion is the location of the image straight line of the given circle Q that passes through the center of inversion and has 0 points in common with the chosen circle of inversion. That is, remember that in this case it is always possible to construct a straight line through the center of inversion, O, that is tangent to the given circle Q, and that tangent to Q through O will partition the parent plane meaningfully into two half-planes. One such half-plane will contain the sample circle Q, and the other such half-plane will not contain the sample circle Q. Consequently, when the power of inversion is positive, then the image of such a circle, the straight line L plus shown in red on the bottom of the board, will be located in exactly the same half-plane in which the original sample circle Q is located. And if the power of inversion is negative, then the image of our circle Q will be the straight line L minus shown in red over here on top, and that straight line will be located in the other half plane with respect to the half plane in which the original circle is located. In other words, when the power of inversion is negative, then the image straight line L minus will be in the half plane that does not contain the sample or the original circle Q. Once you comprehend the statement of the theorem number 19, we suggest that you try to generate a proof of that theorem on your own using the template that we discussed in the previous segments. And before you do that, you may want to watch an animation that I put together for you using the free software called GeoGebra. And in order to make things more fun, we recommend that you try to figure out on your own and explain correctly why the image of the runner point that you will see in a few seconds will be located in one part of the half plane when the power of inversion is positive, and which such image of the runner point will correspond to the power of inversion that is negative. As a guidance to those of our viewers who could not generate the proof of the theorem number 19 on their own, we still use the very same template that we have been using so far. That is, because in this case we are given the center of inversion, the point O, we're given the center of a sample circle Q that passes through the center of inversion and has precisely zero otherwise points in common with the chosen circle of inversion. That point Q is given. Two distinct points define one unique straight line. Through these 2 points, we snap our favorite straight line, lowercase p. That straight line, lowercase p, will intersect our sample circle Q at 2 distinct points. One such point will be the center of inversion. We're not interested in it. The other such point will be diametrically opposite in the circle Q point. We name that point uppercase P. Then, according to our template, quite nicely, we reflect that point into its image under both positive and negative power. We know how to do it. We solve the corresponding problems. We prove the corresponding theorems. The point P will be taken into the point P prime plus, shown at the bottom of the board in red, and under the that's under the positive power of inversion when the power of inversion is positive, and when the power of inversion is negative, then our point P, that is evidently located strictly inside of the circle of inversion, will be taken out and is shown over here, P prime minus, in such a way that the center of inversion O is located where? Precisely in between the original point P and its image P prime minus when the power of inversion is negative. Next, we pick any point A on the circle Q distinct from P. We reflect it in the given circle with both powers. In the first case, this point A will be taken into the point A prime plus when the power of inversion is positive. When the power of inversion is negative, our point A will be taken outside of the circle into the point A prime minus because the power of inversion is negative. Then for all the points in question, I did not designate this over here, but for all the points in question, for the first case when the power of inversion is positive, we write it for the points A prime plus. We will have this relation. We will have the corresponding relation for the points P prime plus, one and the same. Construct the proportion over here and argue that the triangle OAP, which is right Y by construction, is similar to the triangle OP prime plus A prime plus, this guy. Why? Because these two triangles share one and the same interior angle at the center of inversion O. Thus, through the similarity, we argue that the triangle OP prime plus A prime plus must be right, and in that triangle, the side OA prime must be positioned where? Against or lie opposite to the right angle, because in the triangle OAP, the corresponding side OP lies against opposite angle. Likewise, when the power of inversion is negative, we will argue that the angles over here at the vertex O are vertical. Consequently, the triangle OAP and OP prime minus A prime minus are similar, and In similar triangles, again, opposite equal angles lie correspondingly proportionate sides. And again, in this case, the side OA prime minus, in this case, OA prime minus will correspond to the side that lies opposite right angle. Here, that side must be also opposite right angle. So either way, the points A prime plus when the power of inversion is positive, or A prime minus when the power of inversion is negative, will orbit what? They will orbit a set of points from each of which, in some sense, the straight line of centers is seen under one and the same angle, and that angle is right. In other words, any such point A prime plus connected with the corresponding point P prime plus, or any such point A prime minus connected with the corresponding point P prime minus, will form what? A straight line that is perpendicular to our straight line of centers, and thus the conclusion of the theorem follows. The straight line thus constructed will have precisely 0 points with the chosen circle of inversion, and this fact in some sense also follows directly from the theorems that we proved earlier. Remember, when a point that we're trying to reflect in a given circle is located strictly inside, then its image, whether the power is positive or negative, is located where? Strictly outside. And the fact that this outside is strict means precisely that the image point L plus when the power of inversion is positive, or L minus when the power of inversion is negative, will have precisely 0 points in common with the chosen circle of inversion. Game over. Once we understand that proof, we also right away put together an algorithm for Euclidean tools only construction of the image straight lines L plus and L minus. And what is this algorithm? This algorithm pretty much follows our template that we used for a proof of this theorem. Snap a straight line of centers through the points O and Q, obtain the point P, reflected with positive power, reflected with negative power, and once these reflections are known, simply construct a straight line through these points, P prime plus or P prime minus, perpendicular to the straight line of centers that passes through the center of inversion and the point Q. And sometimes I do not tell you explicitly about it, but every time you put a construction together, you need to prove that the construction is correct and does what it claims that it does. And here, for such a proof, again, in the theorem, you see, in this theorem, we proved that these angles, this angle and this angle is right. But in the proof for our construction, we will argue from the fact that this angle is right, because this is how we construct our image. Straight line L is perpendicular, this angle is right, and the straight line L minus is perpendicular. Here, the angle is again right at this point. Once we have this on the box, the angles in the corresponding triangles will be vertical, or in this case, they will be shared with the smaller triangle, and we will take the relationship for the points P prime plus and P prime minus locked into this relationship here equals R squared. From the similarity of the corresponding triangles, smaller triangle, larger triangle, smaller triangle, larger triangle, either way, angles vertical or angle at the point O is shared, these triangles will be similar in similar triangles. The length of the sides about equal angles are in the same proportion. Boom. You construct the proportion, unzip this product over here, and you show that if this is the case, then this is the case, which precisely means that the point A prime is the image of the point A under the inversion of the plane with respect to the circle C with the chosen power, positive or negative. Game over, and the theorem is proved, and we know an algorithm for constructing the image of this type of circles with Euclidean tools alone. According to the theorem number 20 under an inversion of a plane with both positive and negative powers, any circle Q that is concentric with the chosen circle of inversion, C shown white over here, and that is located strictly inside of that circle of inversion. In other words, if our sample circle Q has the center at the center of inversion, but its radius, uppercase R, is strictly less than or smaller than the radius of inversion R, if we agree that with the COR we designate precisely the circle of inversion, where the point O is the center of inversion and R is the radius of inversion, then under these conditions, regardless of the power of inversion, positive or negative, such a circle will be taken into another circle, Q prime, that will also be concentric with the circle of inversion, and it will be located strictly outside of the circle of inversion, or algebraically, the radius, the uppercase R prime of the circle Q prime, which is the image of our circle Q concentric with the circle of inversion, will be strictly larger than the radius of inversion R, and that algebraic situation is captured on the left hand side of your screen, where again the circle of inversion C is shown in white. This is the circle of inversion. The point O is the center of inversion. Our sample circle Q that also has the center of inversion as its center and is located strictly inside the chosen circle of inversion is shown in green over here. This is the circle Q, and the image of that circle, again regardless of the power of inversion, positive or negative, is the circle Q prime shown over here in red, and as we can see, it is also concentric with the chosen circle of inversion with the sample circle Q, but that image circle Q prime is located strictly outside of the circle of inversion, strictly outside of the circle of inversion. Again, once you comprehend the statement of this theorem, we suggest that you try to generate a proof of that theorem on your own, and in order to help you, I'll put together an animation using the free software called GeoGebra that precisely captures the heart and soul of the technical essence of the theorem number 20. It is not that difficult to construct a proof of the theorem number 20 if, for example, we pick an arbitrary point, let's say the point A on the circle Q. This will be our point A on the circle Q, and then we reflect that point in the given circle with, let's say, positive power into the point. Let's say here we will reflect it into the point A prime plus, for example, or with negative power. When the power of inversion is negative, we know that the image of such a point will be located on the other side of the center of inversion. So here we will take that point to the opposite side, and it will go here, and this will be our point A prime minus. Either way, what will we have for all of these points? Well, first of all, we have the distance from the center of inversion to the point A is strictly less than r, and this is what we call our radius of the circle Q, that distance right here. And for either point, the image of the given point A when the power of inversion is positive, or the image of the given point A when the power of inversion is negative, we will either way have one and the same relation. OA times OA plus is equal to R squared equals to OA times OA prime minus. It doesn't really matter. And what does it mean for this distance right here? This distance and this distance. If this distance over here is known to us, it's uppercase R, and this distance over here is uppercase R. Well, either way, because this distance is one and the same, we will have for the point OA prime plus, and for the point A prime minus, we will have one and the same expression, R squared divided by R. This will be a constant, and we will refer to it as R prime precisely. This is the radius of the circle that is located strictly outside of the circle of inversion. And how can we see that? Well, because in our relation, remember, uppercase R is strictly less than R. And what does that mean? Well, that means that R divided by R is strictly larger than 1, and then R square over R is equal to R times lowercase r, and that is always larger than R. That string of manipulations is quite straightforward, and voila, regardless of the power of inversion, be that power positive or negative, the image of the circle Q that is concentric with the chosen circle of inversion C will be a circle that is also concentric with the circle of inversion C, that circle right here shown in red, Q prime, but that circle will be located strictly outside of the chosen circle of inversion. Again, why is that? Because the point A was chosen on the given circle Q at random, and that means that all the other points that are the images of any other points that we pick on that circle will obey one and the same, this condition right here, and that is precisely the definition of what a set of points in a given plane, the distance from each of which to the fixed or chosen point O is one and the same, and that is definition precisely of a circle, and that proves this particular theorem. And again, once we understand how the proof of this theorem works, the Euclidean tools only construction of the image circle Q prime, in this case located strictly outside of the circle of inversion, is more than straightforward. Given our concentric circle Q that is located strictly inside of the circle of inversion and concentric with it, pick any point on that circle Q, A. Reflect that point in the given circle. At this point, it doesn't really matter. Pick your favorite power, with positive power or negative power, into the point that you name accordingly. That's it. Game over. Put the needle of the compass in the center of inversion. Open up your compass to this distance, A prime plus or A prime minus, and draw a circle, and the circle thus constructed will be precisely the image of the given circle Q that is concentric with the circle of inversion C and is located strictly inside of the circle of inversion. And it is now evident that the next theorem, the theorem number 21, will look at the Opposite situation when our original circle is concentric with the circle of inversion C, but is located strictly outside of that circle. According to the theorem number 21, under an inversion of a plane with either power, positive or negative, any circle Q that is concentric with the given or chosen circle of inversion, C shown in white over here, and that is located strictly outside of the circle of inversion, outside of the circle of inversion. In other words, the radius of our sample circle that is concentric with the chosen circle of inversion is strictly larger than the radius of inversion. Again, we take it that the symbol COR designate the chosen circle of inversion. Then, under these conditions, that circle will be taken into a circle Q prime, that will also be concentric with the circle of inversion C. That circle here is shown in green, the image circle this time in green, and that will be located strictly inside of the circle of inversion. In other words, the radius uppercase R prime of our image circle Q prime will be strictly less or smaller than the radius of inversion lowercase r, and again O in all cases, O in O. The center of inversion designates the center of all the circles. In other words, all three circles in question in this case are concentric. And once you understand the statement of this theorem, we suggest that you try to generate a proof of that theorem on your own. And in order to help you do that, you may watch an animation that I put together for you using the free software called GeoGebra. If you understood the proof of the theorem number 20, then you should be able to construct the proof of the theorem number 21 on your own without any problems, because in this case we just have to flip the relevant signs to their opposites and roll through the corresponding string of manipulations in exactly the same way. If we pick an arbitrary point or a random point A on the given circle Q, shown in red over here, that is concentric with the circle of inversion, C shown in white, and that is located strictly outside of that circle, meaning that the distance from the center of inversion to such a sample point is strictly larger than the radius of inversion. Uppercase R is strictly larger than R. Then again, regardless of the power of inversion, be that power positive or negative, we reflect that point in the chosen circle into the point A prime plus if the power of inversion is positive, or the point A prime minus if the power of inversion is negative. We know in this case the center of inversion, the point O, will be in between the pre-image point A on our circle Q and the image point A prime minus. And in the first case, when the power of inversion is positive, that point will be on the same side of the center of inversion. It doesn't really matter. But the string of manipulations or the condition 3 of definition 1 will be rendered algebraically in exactly the same way. The relevant product are equal to the square of the radius of inversion r. And again, we deduce that the distance from the center of inversion to either image, a prime plus or a prime minus, must be actually one and the same. Why? Well, the radius of inversion, lowercase r, is constant. Its square is constant. The radius of the simple circle that is concentric with the circle of inversion and is located outside of it, uppercase r, is also constant. A constant divided by a constant is exactly a constant, and it is that constant, uppercase r prime, is what we call the radius of the image of our circle Q, or larger circle Q. And what do we call the set of points in a chosen plane, each of which is equally distant, exactly equally distant from one fixed point? Precisely, we call that set of points a circle. Consequently, we obtain our circle Q prime, that is green and shown over here, and that circle will be located strictly inside of the circle of inversion C. Why is that? Well, in this case, uppercase r is strictly larger than the lowercase r, or the radius of the red circle Q is strictly larger than the radius of the white circle C, the circle of inversion. And that means that the ratio of the length of the radius of inversion to the length of the radius of the sample circle located outside of the circle of inversion will be what? Will be strictly less than 1. And then our ratio lowercase r squared over uppercase r can be represented what, as a product of the length of the radius of inversion, lowercase r, times the ratio, which is itself always less than 1. Hence, a strictly positive real number multiplied by another real number that is less than 1 will make the original number smaller, and that means that this product will be strictly less than the length of the radius of inversion. And that precisely means that this algebraic fact translates back into English as follows. The image of the circle Q that is concentric with the circle of inversion and is located strictly outside of it is a circle that is also concentric with the circle of inversion, but that circle is located strictly inside of the circle of inversion. And now that we're done with the preparatory theorems, we can move on to the so-called fundamental theorem of inversive geometry. In the theorem number 22, or the so-called fundamental theorem of inversive geometry, or a theorem to which we will be referring as ICSTT for inversion of the real plane with respect to a circle similar triangles theorem, we're given the following setup. If the points P prime and Q prime are the inversive images of the points P and Q correspondingly, and the pre-image points P and Q honor or satisfy the following three constraints. The points P and Q are distinct. That means that the point P is not the point Q and the point Q is not the point P. That's number one. Number two, neither the point P nor the point Q is the center of inversion, or the point O in this case, and the point at infinity. And the constraint number three, the center of inversion, the point O, and the points P and Q are not collinear. They do not belong to one and the same straight line, for example, lambda. Then, under these conditions, the following triangles, the names of the vertices of which in the formation of these triangles is important and cannot be changed, are similar. That is, the triangle OPQ, where the order of the vertices OPQ is what it is and cannot be changed, is similar to the triangle OQ prime P prime, where again the order of the names of the vertices in this triangle, the vertex O followed by the vertex Q prime followed by the vertex P prime, is important and cannot be changed. And by the end of the proof of this theorem, we will understand why and what does that mean. In order to help you generate a proof of this theorem on your own, I've put together an animation using the free software called GeoGebra, and in that animation that you're about to see, I let the pre-image points P and Q run about a little bit in the parent plane, then I stop them, then I let run them some more, then I stop them again, and I do that several times. And the reason why I do that is because I want to give you an opportunity to see why the angles in these two triangles vary the way they are, and that hopefully will help you understand what is going on and, most importantly, why. Now, before we discuss a proof of this theorem, which is not that complicated, I would like to observe that from the statement of this theorem, it follows that that theorem applies to both powers, positive, as shown over here, and negative, so long as we all understand the following caveat, because now we have two independent objects, the pre-image point P and the pre-image point Q, which can be reflected in a given or chosen circle, shown partially over here as the circle of inversion C. We technically do not really need its presence, but I show it here to be complete, to show a complete description of the situation. We can have the points, for example, P and P prime, be the inversive images of each other under the corresponding inversion of the real plane with respect to a chosen circle with, let's say, positive power. But we can reflect the point Q in a given circle. Everything else remains the same, but in negative power. No one can prevent us from doing that. In that case, when the powers under which the points P and Q are reflected in a given circle disagree, then the theorem 22 does not hold. That much we all have to understand. In other words, the theorem number 22 holds so long as both images P prime and Q prime are obtained as the power of inversion is fixed and one and the same. In other words, that power could be positive for both images P prime and Q prime, or that power could be negative, but it has to be negative for both images P prime and Q prime again. And here, for demonstration purposes, I will present a proof of the theorem number 22 when evidently the images P prime and Q prime are obtained by reflecting the points P and Q in a given circle with positive power, but the technical essence of the corresponding proof when the power of inversion is negative remains exactly the same, with the only difference that when we flip the points P prime and Q prime on the other side of the center of inversion, what will we have? Well, we will have not the angle that is physically shared, but we will have two angles that are vertical. But the magnitude of this angle over here at the center of inversion will remain the same. And another detail I want to mention is that in my book and in this course, I laid out the proofs of all the theorems that lead up to the theorem number 22 in that particular order, in order to demonstrate that it sometimes so happens that in mathematics the importance of a certain theorem is not really evident right away, but it only emerges with time. And again, I have talked about the theorem 22, and it's important for a long time. The proof of this theorem over here is basically a baby proof, nothing beyond the middle school curriculum in Euclidean in geometry. And the thing is, we saw all the tactical maneuvers that we're about to pull in this proof already prior in the previously proven theorems, which were carefully orchestrated, of course, by me. In this case, we were dealing with mostly right triangles. Here we have two arbitrary triangles. They do not have to be right, but the technical essence, the underlying argument of why this theorem is true and correct remains exactly the same. That is, if we're given two inversive images, the points P prime and Q prime, then stepping away from the specific geometry and into the algebraic manipulation, we pull up the condition number 3 from the definition 1 of how we define this geometric transformation, and we have the product of distances of the pre-image and image points P with respect to the center of inversion that must be equal to the square of the radius of inversion of our circle shown in white over here. And that square of the radius of inversion must also be the product of the distances of the other point Q and Q prime with respect to the center of inversion. That must be true. And now we carve up, or we restructure, the equality of these two products, the two-factor products, in a way that is tactically advantageous to us. This is not the only way to do it, and in a few seconds we will see how this can be done in yet another way when we'll be looking at the second corollary of this theorem as it applies to negative powers of inversion. But here we do it in a way in which we did it many times already. We grab the distance from the center of inversion to the second, let's say, pre-image point Q. We move it from the right-hand side of this equality to the denominator of the left-hand side, and we construct a ratio of the distances from the center of inversion to the point P and from the center of inversion to the pre-image point Q. And at the same time, we grab this rightmost factor on the left-hand side of the equal sign, and we move it into the denominator of the right-hand side. And here we form the following ratio: the distance from the center of inversion to the image point Q prime over the distance between the center of inversion and the image point P prime. And here already we see that the angle at the vertex that both of these triangles share, which is the center of inversion, in this case I designated it with the point O, the angle alpha is physically shared by the two triangles specified in this theorem. The angle alpha, I refer to this angle alpha. This angle is rendered over here algebraically. Here again, the order of the names of the vertices in the formation of the angle is important. I will explain why in a few seconds. but by the corresponding theorem in Euclid's Elements. I think it is book 6, proposition 6, if I'm not mistaken. By modern terminology, this will be what? Side angle side, by the SAS criterion. These two triangles similar. So as we can see, the proof is not very complicated. It's very straightforward. Basically 2 steps. Write down the workhorse formula for the points for the inversive images, construct the right ratio, observe that the angle, in this case when the power of inversion is positive, is shared, make a conclusion that the triangles are similar, and now turn around and bring up the other theorem. Again, in Euclid's Elements, if I'm not mistaken, that would be book 6, proposition 5. In similar triangles, equal angles lie opposite correspondingly proportional sides. And now here we need to be careful, and that is where the order of the vertices in the names of the triangles and the corresponding angles becomes important. Here we see that, for example, in the triangle to which I referred as OPQ, we have the angle QOP equal to the angle P prime OQ prime, P prime OQ prime. And here is the gist of it. When I said early in the previous segment, when I formulated the premise of this theorem, when I said that the order of the names of the vertices in the formation of the triangle cannot be changed, that means that it cannot be changed for the duration of the statement. If we name the first triangle, let's say, as OPQ, then the other triangle has to be named in this particular order. This may be deviation from what most high school and middle school students are used to, but here the following fact becomes important. If we agree that to every planar Euclidean angle we attach not 1 but 2 attributes, the first such attribute will be the magnitude, and that is what most students are accustomed to, but the second attribute will be direction. And here, mathematically, the notion of direction can be defined in a number of different ways. Here is one way to deal with it. For example, let us say that in our triangles, again, it doesn't really matter. Some initial choices will be arbitrary. And for demonstration purposes, our arbitrary choice is the following. We want to visit the angles in all of these triangles in the following order. First, let's say we start with alpha, then we move to beta, and then we move to the angle gamma. If we want to visit, and again, I want to make sure that everyone understands this choice is arbitrary, just because we can pick any other choice, initial choice, the order in which these angles will be visited. But once we fix that, the magic of what is going on here in inversive geometry will be one and the same. So here, if we want to visit the angles in the triangle OPQ in this particular order, alpha followed by beta followed by gamma, then how do we have to walk the perimeter, let's say, of this triangle? Well, we have to walk the perimeter of this triangle OPQ in such a way that our right hand will always be in the triangle, but the left hand will be always outside of that triangle. And again, for various fabulous historical reasons, people refer to this direction of walking as what? As clockwise. But if we want to visit the angles of the other triangle, OQ prime, P prime, in the same order, how do we have to walk the perimeter of that triangle? Well, we have to walk the perimeter of this triangle in such a way that our left hand will always be in the triangle, but the right hand will be sticking out of the triangle. And here we will walk the perimeter of this larger triangle as from the point O towards the point Q prime, and then from the point Q prime we will hit the angle gamma, visit the point P prime, and then we'll come back to the center of inversion, or the point O. And that precisely means that while this equality, or all three equalities shown over here, capture what? They capture actually both things. They capture first the fact that the magnitude of the angle at hand is equal all the time for the corresponding pairs. And why is that? Well, because again, remember the theorem which states that in similar triangles, opposite to angles of the same magnitude lie correspondingly proportionate sides. And let's look at our triangle to which we refer as OPQ. OPQ. In this triangle, the side OP corresponds to which side? OQ. And in the smaller triangle, or let's say pre-image triangle, the side OP lies against which angle? Opposite the angle gamma. And that means that in the larger triangle, or in the image triangle, the side OQ, this side must also lie opposite this angle gamma. So the angle gamma is right here, and we capture this fact over here. And the angle beta. What's going on with the angle beta? In the pre-image triangle OPQ, the side OQ is opposite angle beta, or angle beta lies opposite to the side OQ, and the side OQ in the pre-image triangle corresponds to the side what? OP prime. OP prime. So this side must lie opposite the angle beta, or the angle beta must be opposite to the correspondingly proportional side. And that is why we have the magnitudes of the angles alpha, beta, and gamma equal the way they are across two arbitrary triangles, as long as our usual suspects, the pre-image points, satisfy 1, 2, 3 constraints. Now, what in this algebraic expressions, what else is going on, and what tells us that the direction of the angles at hand is opposite in both cases? Well, precisely the order of the names of the vertices. And what is going on over here, if we carefully look at the way we name the angles in all three cases for the angle alpha, beta, and gamma, we will see two things. First, it may be tempting to say, okay, the point P prime is the image of the point P, and the point Q prime is the image of the point Q, so why don't we simply mechanically replace the pre-image points in the other triangle with their direct images? So this angle over here, QOP, should have been, or why not, name it Q prime, P prime. But no, here we did not do it this way. We, in a sense, correlated the letters in this, the names of the vertices in this angle as Q prime, P prime, but then we swapped. You see, we swapped the names of the vertices that form that angle. Again, that is the first thing that is going on. And if you look carefully at the names of all the vertices, that is exactly what happens. P and Q are named P prime, Q prime, and then they're swapped, Q prime, P prime. And here the letters, the vertices P and Q are also taken into their images, P prime, Q prime, and then they're swapped, Q prime, P prime. So the first thing is we take the images and then we swap them with respect to the names of the pre-images. And the second thing that is going on is here technically there comes in a little bit of, let's say, theory of groups or theory of permutations, because in the theory of groups it is shown that the permutations of a finite number of objects forms the so-called finite symmetric group Sn, the size of this group is n factorial, and the permutations that form that group come in two flavors: even and odd. Odd permutations do not form a group, even do, and they even permutations form the so-called alternating group AN. The size of this group is n factorial over 2, but we do not need to dive too deep into the theory of groups over here. What we do need to understand, or steal a little bit from the theory of groups, is that what we have here in the names of the angles of the in the corresponding triangle is called a cyclic permutation. And the way this, in this case, it's the so-called three cycle, because we have three distinct elements in each name over here. And the way this three cycles are created is as follows: the letter Q is put behind the letter P, and this is exactly what we have. If we put Q behind P, we have what? OPQ. And now we grab the letter O and we put it behind letter Q, and we have PQO. And we can go on like this. We now grab the letter P, put it behind letter O, and we come back to this QOP, and we can go in cycles like this forever and ever. Same exact deal applies to the names in these angles over here. P prime goes behind Q prime, O, Q prime, P prime, and here O goes behind P prime, Q prime, P prime, O. This is how these angles are formed. And again, remember that if we want to walk our angles, visit the angles in each triangle in a specific order, we can now understand this is just one instance of a three permutation, the cyclic permutation. We can put the angle alpha behind gamma and visit the angles beta, gamma, and then alpha, and so on. But the fact that the direction of the angles will change to its opposite when we jump from one triangle to another, pre-image to image or image to pre-image, that fact will remain one and the same. And the conclusion that we draw from this experiment is that while the magnitudes of the angles are preserved by the geometric transformation of inversion, in other words, inversion of the real plane with respect to a circle, regardless of the power, preserves the magnitudes of the angles. And in general, in grown-up mathematics, this type of mappings are called conformal. But the caveat here is that the situation is slightly more delicate. In other words, one attribute, the magnitude of an angle, is not enough. We need to introduce another one, the direction. And here, as we saw, the direction of the angle is flipped, of each angle is flipped to an opposite. And with this technical caveat understood, the inversion of the real plane with respect to a circle, that is y, as a mapping of the real plane onto itself, is called anti-conformal, and that is precisely the meaning of anti-conformal. The magnitudes are the same, but the directions are flipped to the opposite direction. Just let's grab one angle, for example, the angle alpha. The way we form the name of that angle with the corresponding vertices of our triangle is what? From Q to O to P. So we put the names of the vertices into that angle. When we walk about the triangle, in which way? Well, clockwise, because our right hand is in and the left hand is out. But the same angle in the corresponding image triangle will be formed which way? From P prime to O and to Q prime. And that means that when we walk the perimeter of this triangle in the order in which we visit the vertices, our left hand will be in and the right hand outside of the triangle. And that is precisely one way to define direction. And it is important to understand that, again, the magnitudes of all the angles under the inversion of the real plane with respect to a circle with the same power, when the power is consistent, is preserved, but the direction of all the angles under the inversion of the real plane with respect to a circle, regardless of power, if that power is consistently the same, is changed to the opposite. And that is why the name of the mapping that we're studying, inversive geometry or inversion of the real plane, is called anti-conformal. And we're pretty much almost done with the proof. We just have to button up a few things here. Look, we have three, how many cases we have? Let's count. The points P prime, the images, and Q prime are located outside of the circle of inversion. We covered that. The second case we have when the points P prime and Q prime, the images, are inside the circle of inversion. That's the second case. And then we can swap the location of the first point with respect to the other one and the other one with respect to the first one. So we have four cases. We covered one. So let us, in an expedient manner, go over the remaining three cases. If, with respect to the proof that we generated in the previous segment, we throw the image points P prime and Q prime strictly into the circle of inversion C, shown in white over here partially, then that means what? By the corresponding theorem, that means that the pre-image points Q and P will be outside, strictly outside of the circle of inversion. And here the only tactical maneuver that we have to do is captured over here on the right hand side of your screen. Uniformly or consistently throughout all the reasoning that we generated in the previously shown proof, we replace the letter P with the letter P prime and the letter P prime with the letter P. And just as uniformly and consistently at the same time, we replace the letter Q with the letter Q prime and the letter Q prime back with the letter Q. And that means that in this case, the names of the triangles will change. Our triangle OQP will be similar to the triangle OP prime Q prime. Why is that? Well, again, if we keep the ordering of our angles in which we visit these angles in our triangles from alpha to beta to gamma, then this is precisely the ordering that we have: OQP, OQP, where the vertex Q designates the angle beta and the vertex P prime designates the angle beta over here. You see, this is the correlation. Likewise, the vertex P is associated with the angle gamma, and the angle gamma in the image triangle is associated with the vertex Q prime P. The algebra here remains the same. The ratios remain the same. The names of the triangles now are what they are. They flipped. And all the names of the angles are adjusted accordingly. I will not go over the details of these names. Put this video on pause and keep me honest, verify. But what the essential point that must be taken away from here is the following. Again, the magnitudes of the angles under the inversion of the real plane with respect to a circle, in this case with positive power, the magnitudes are preserved, while the directions of all the angles are changed to their opposite, and in the sense in which I explained earlier, where we can define the direction by which hand is inside the triangle and which is outside as we walk the perimeter of the triangle at hand. Consequently, if we name the angles, the vertices of the angle in exactly the same way, then we will see that if the angle For example, alpha is named in the order POQ from P to from P to O to Q. Then in the image triangle, we go from the vertex Q prime to O to P prime. One direction, and then what is this? POQ. One direction for the pre-image triangle, and another direction QOP prime for the image triangle, and so for all the angles. And now we will alternate the positions of one pre-image point. We will throw one pre-image point inside of the circle of inversion and the other one outside of the circle of inversion. In the third case, if the pre-image point P is located strictly inside, while the pre-image point Q is located strictly outside of the circle of inversion, see the white circle of inversion shown over here, then with respect to our original proof, we uniformly or consistently touch only the letter Q. In other words, in that proof, uniformly, consistently, and mechanically we replace every occurrence of the letter Q with the letter Q prime, and conversely, every occurrence of the letter Q prime with the letter Q. Then the technical essence of the theorem will still hold, and in this case, the names of the triangles will be assigned as follows. The triangle OQP prime will be similar to the triangle OPQ prime. Why is that? Well, if we follow the algebra, look at the shared angle, and then make a conclusion about the fact that these triangles are similar, and use the other theorem that opposite equal angles lie correspondingly proportionate side, then we will see again in the triangle OQP prime, we visit the angles in the agreed upon order. Again, this is arbitrary decision. You can change it. It can be changed, but then correspondingly all the letterings will have to be changed. But the fact will not change that in this case we visit the angles in this triangle from alpha to beta associated with the vertex Q, and then to gamma associated with the vertex P prime. Likewise, in the triangle OPQ prime, we visit the angles from O to P beta, and then from P to Q prime gamma. Again, I changed the names of the angles alpha, beta, gamma correspondingly. You should keep me honest and verify. But in this case, again, these relations shown over here prove that under the inversion of the real plane with respect to a circle, this time with positive power, both times the point Q is reflected in the given circle with positive power, and the point P is reflected in the circle C with positive power. The magnitudes of all the angles remain the same, but their directions, the direction in which we form these angles, changes to the opposite. And now we will look at the fourth and the final case, where we will throw the pre-image point Q inside of the circle of inversion, and the pre-image point P will be outside of the circle of inversion. In the fourth and the final case, when the pre-image point P is located strictly outside and the pre-image point Q is located strictly inside of the white circle of inversion, C, shown partially over here, then with respect to our original proof that we generated earlier, we roll through that proof and uniformly, consistently, and mechanically replace every occurrence of the letter P with the letter P prime, and we replace every occurrence of the letter P prime with the letter P we leave the letter Q alone. We do not touch it, as we keep it as it was. Then, in that case, the similar triangles will be named as follows: OQ prime P, OQ prime P, in this case OQ prime P, because again, by now we understand in this triangle we traverse or visit the angles in our cyclic fashion from the angle alpha towards the angle beta, towards the angle gamma, towards the angle alpha. And that triangle will be similar to the triangle OP prime Q. O, P prime, and Q again, because in this triangle we visit the angles in exactly the same cyclic order, from the angle alpha to the angle beta to the angle gamma to the angle alpha again. The corresponding algebra here and here will remain probably, well, here it will remain the same. We may have to adjust things over here, but the conclusion that we will draw, because the angle alpha is shared, and we carefully look at which sides lie opposite equal angles. This will be the similarity of triangles. OQ prime P will be similar to the triangle OP prime Q. I changed the names of the angles over here. In this proportion, probably you have to adjust things accordingly. But again, the fact that we now changed the mutual juxtaposition of the pre-image points with respect to the circle of inversion, we now split them apart in a different way, will not change the essence of our statement. Still, the magnitudes of the corresponding angles will be still one and the same as shown over here, here, and here, so the angles will be preserved in this case, but the directions in which we form these angles and name the vertices of these angles will change to the opposite, as we explained earlier. And now we're done with the theorem 22. We now understand why, as a mapping of the real plane into itself, inversion of the plane in a circle is called anti-conformal. One more time, precisely because under the inversion of the real plane with respect to a circle, when the multitude of objects is reflected in the chosen circle in the consistent power, positive or negative consistently both times, the magnitudes of all the angles remain the same or are preserved, but the directions of all the corresponding angles are changed to their opposites. The first low-hanging fruit corollary of the theorem number 22 is the following. When the power of inversion is positive, as is shown with the blue plus sign over here, then we know that all the image and pre-image points under the inversion of the real plane with respect to a circle and so on are thrown on the same side of the center of inversion. In this case, I show the center with the letter O. Then we just proved in the theorem 22 that in our corresponding triangles, no matter how we name the vertices of these triangles, as long as we have two pairs of points that satisfy the three constraints of the theorem 22, then we prove that, for example, this angle beta is equal to this angle beta by magnitude, and this angle gamma, let's say, is equal to this angle gamma by magnitude, not by direction. It doesn't really matter for us. Working with magnitudes alone, what does it mean? Well, it means that on the other side over here, we have the angle whose magnitude is what? Pi minus gamma. And on the other side of this angle beta, along this straight line, what do we have here? Well, we have another angle that is equal by magnitude to what? Pi minus beta. Now what do we have? Well, we have two opposite angles whose magnitudes are what? Beta plus pi minus beta and plus positive beta cancel out. We have the two angles that sum to pi. And likewise, for this angle, we have pi minus gamma plus gamma minus gamma plus gamma cancel each other out. The magnitude of these two opposite angles sums to pi. And what does that mean? That means precisely that the points of interest, whatever we name them, Q, Q prime, P, P prime, or in any other legal permutation, these points are concyclic, precisely. And that means that the 4 points of interest that are the bread and butter of the theorem number 22 are concyclic, and they form a quadrilateral that is cyclic. In other words, all 4 points of interest sit on one and the same circle that I showed here in dashed blue, and that is the first corollary. Think on your own what the second related corollary might be. The second related low-hanging fruit corollary of the theorem number 22 comes about if we consider the negative power of inversion. Not the positive one as we did in the previous segment, but the negative one is shown with the minus sign. Then, in this case, we will take it that in the theorem 22 we proved that our observation that the triangles O, P, Q and the triangles O, Q prime, P prime are similar with the corresponding angles traversed in the same direction, for example, from the angle alpha to the angle beta to the angle gamma, here from the angle alpha to the angle beta at the vertex Q prime to the angle gamma to the vertex P prime. Again, in the previous case, I did not really show the specific names of how we name the inversive images. It doesn't really matter here. I did it just for demonstration's sake. So let's say our pre-image points P and Q are located strictly inside of the circle of inversion, here shown in white. This guy shown in white. And under the inversion of the real plane with respect to this circle with negative power, these points are thrown on the opposite sides of the center of inversion. The point P is taken into the point P prime located strictly outside of the circle of inversion, and the pre-image point Q is thrown into the point Q prime that is also located strictly outside of the circle of inversion and on the other side of the center of inversion. Then our theorem 22 is applicable to our favorite triangle O, P, Q, O, Q prime, P prime. That much we proved. But we can also connect the points Q prime, and the point P, the pre-image point P. Likewise, the image point P prime, we can connect it with the pre-image point Q. And we will form 2 other triangles, which I cross-hatched a little bit here and there at the risk of making this diagram messy. But if we start with our favorite condition 3 definition 1 workhorse formula, because here it's what the square of the radius of inversion from this equality, we in the previous proof, in the actual proof of the theorem 22, we carved up, or we restructured this equality, which we took the distance OQ from the right hand side and put it into the denominator of the left hand side, and we stole the distance OP prime and moved it to the right hand side from the left hand side. Here we carve up exactly the same relation slightly differently. We steal the distance from the center of inversion O to the image point Q prime, and we move it from the right hand side to the denominator of the left hand side. This is the fraction that we form. Likewise, from the left hand side, we do what? We steal the distance from the center of inversion to the image point P prime, and move it from the left-hand side into the denominator of the right-hand side. And then we apply it to these triangles over here. So once we carefully analyze which angles lie opposite which sides, then we will conclude that in this case the triangles OPQ prime, OPQ prime, where again the order of the names of the vertices in the formation of the name is important. For the duration, this cannot be changed. These names, the order has to be locked. This way is similar to the triangle OQP prime. OQP prime. Here again we have quite a bit of angles. I kept the angles alpha from the previous proof the way it was, the angle alpha, beta, gamma, alpha, beta, gamma. But in these two triangles, the triangle OPQ prime and OQP prime, we have the other pair of angles, what, vertical, and hence of equal magnitude. I designated these angles delta and delta. And again, through this proportion, we show that the lengths of the sides in these two triangles about angle of the same magnitude are in the same proportion. These angles must be similar. Once we go through the same motions, we will see that this must be the case. So if we name the angles of this other pair of similar triangles as phi, theta, and delta, then again, from this designation of the order of the names of the vertices, we see that the triangle OPQ prime, we traverse in which direction? Delta, phi, theta, and then in the similar triangle OQP prime, we traverse the angles in the same direction, delta, phi, theta. Wonderful. Now, what do? Well, we grab any angle that contains a complete diagonal of our quadrilateral. Let's say we name it Q, P, Q prime, P prime. Let's say we take the triangle Q prime, Q, and P. Doesn't really matter. By Euclid's Elements, Book 1, Proposition 32, the magnitudes of the interior angles of every non-degenerate plane, a Euclidean triangle, sum to pi radians. So there we go. We sum the angles in this triangle one by one. So what do? Theta plus phi plus beta plus gamma must be pi by that theorem, because here the angle at the vertex P in our quadrilateral is composite. It's composed of two angles, phi and beta. That's wonderful. But now we look at the same quadrilateral from the standpoint of opposite angles. What's going on? Well, the angle at the vertex Q prime, it is composite. It is composed from two angles, theta and beta. Theta and beta. And what's the opposite angle composed of? Gamma and, oh, look at this. What a wonderful gift. Phi, the angle phi, gamma plus phi. Gamma plus phi, pi. Wonderful. Now, the other pair of opposite angles at the point P, at the vertex P prime and at the vertex P. What do I have at the vertex P prime? Theta plus gamma. Theta plus gamma. What's the opposite angle? Phi plus beta. Phi plus beta. Again, pi. So if the magnitudes of the opposite angles in the quadrilateral sum to precisely pi radians, what does that mean? That means precisely that these vertices, that this quadrilateral is cyclic. It means that the 4 points at hand are concyclic, and that means that in this case, even when the power of inversion is negative, still we have a property that is similar to the one when the power of inversion was positive. That is, the image points, again, if we torture this configuration to death by cyclically permuting the names of the corresponding points, once we throw them inside, outside, try all the legal permutations, we will still see that the 4 points of interest, the pre-image points, let's say in this case Q and P and Q prime and P prime, still belong to one and the same circle. Here is my artistic rendering of that circle shown in blue and dashed line, but you guys understand what is going on. These 4 points are still concyclic. They belong to one and the same circle, even when the power of inversion is negative. According to the theorem number 23, under an inversion of a plane with respect to a circle named C and shown over here in white partially, that has the point O as its center and lowercase r, a strictly positive real number, as its radius with positive power, as is shown with the plus sign in front of the square of the radius of inversion with positive power. Any circle Q that does not pass through the center of inversion and has precisely 2 distinct points in common with that circle of inversion, that any sample such circle Q is shown in green over here, this is the circle with the smaller radius, is taken into a circle Q prime that also does not pass through the center of inversion, just like the pre-image circle, and that passes precisely through the same 2 distinct given common points between the pre-image circle Q and the circle of inversion C. Think about how you would symbolize this fact that if the circle Q does not pass through the center of inversion and has 2 distinct points in common with the circle of inversion, the image circle Q prime also passes through exactly the same common points. Compare your ideas to ours, and in order to help you generate a proof of the theorem number 23, which by the way evidently should use the results of the theorem number 22, I put together an animation using the free software called GeoGebra, which captures the technical essence of the theorem number 23. One way to generate a proof of the theorem number 23 is to go back to our templates that we worked with in the previous proofs and basically replay the same script again. That is, we take the center of the given circle Q that does not pass through the center of inversion. We take the center of inversion because both are given, both of the circles are given, both of the centers are given. And through these 2 centers, we construct the straight line of centers. Now, unlike the previous cases when our given circle Q was passing precisely through the center of inversion, this time that circle does not do that. And that means that the straight line of centers, we usually named it P, this time I did not give it a specific name because it's not that important, will intersect our given circle Q at 2 distinct and diametrically opposite points, each of which will be distinct from the center of inversion. That is, let us agree that the straight line of centers will intersect the given circle Q at 2 distinct and diametrically opposite points named A and B. Next, what's next? Well, we reflect these points A and B in the given circle with the given power. If, let's say, the point A was located strictly inside of the circle of inversion C, shown partially in white, then it will be thrown outside into the image A prime. Likewise, if the point B was located outside of the circle of inversion, this reflection will take it strictly inside the circle of inversion into the point B prime. Wonderful. So what was the next step in our template that we used to prove the theorems 15 through 19? We grab an arbitrary runner point, let's say C, on the given circle, arbitrary. That should be technically distinct from the points A and B, for example, this one. And what do we do with this point? We reflect the point C, the sample runner that belongs to the given circle Q, in the given circle with the given power into where? This straight line that connects the center of inversion in C will evidently intersect the given circle Q at least more than one time, for example twice, but because this point is located inside of the circle of inversion, then the uppercase C letter will be taken outside into this point right here, C prime. And now we begin constructing our angles. First, we know that when the power of inversion is positive, then the points that are in common between the given circle Q and the circle of inversion, we can even name these points if you wish, for example, F1 and let's say F2 are taken what? Based on the theorem number 1, these points will be fixed or stationary. They will be taken into themselves. Thus, we know that no matter what is the mystery curve into which the circle Q is taken, this mystery curve must pass through the common points F1 and F2, and consequently, we know once we reflect the point A into its image A prime and B into the point B prime, there is also what will happen is that the mystery curve, we do not know what this mystery curve is, but it has to pass through these points also, A prime, B prime, F1, F2. And now we bring in the heavy artillery, so to speak. We bring in our fundamental theorem of inversive geometry, the theorem number 22, and we apply this theorem to two pairs of points. Look at this, the point A and the point C, they satisfy the conditions of the constraints of the theorem 22. These points are distinct. Both of these points are different from the center of inversion and the point at infinity. They're not collinear with the center of inversion. So what does it tell us? Well, here is the first result. The magnitude of the angle OCA must be what? We don't even have to look. We know what we have to do. This magnitude of this angle will be equal to the magnitude of the angle OA prime. We swap the letters, OA prime, C prime, this angle. I named it gamma here and here. OCA, OA prime, C prime. This is what's captured over here. Wonderful. We now apply the theorem 22 to another pair of points that satisfy the constraints of that theorem, and these points are what? B and C again. So what do we have now? The angle, the magnitude of the angle OCB, this angle right here, must be, which I refer to as beta just for the sake of brevity, must be equal to what? To the magnitude of the angle OB prime, C prime. So we see that here we take the vertices of this angle into their images, C prime and B prime, and then we swap them, remember. Correlate directly and then swap, and this is exactly what we have. So the magnitude of the angle OCB and the magnitude of the angle OB prime, C prime is the same. And essentially this is it, the game is over. The angle OCB is composite. It is comprised of the which angles? OCA, which is gamma, OCB, is gamma plus what? Plus the magnitude of the angle ACB. But the angle ACB is the circumference angle that subtends the semicircle, subtends the diameter of the circle Q right here, AB. Hence, the magnitude of that angle is what? Pi over 2, 90 degrees. Gamma plus pi over 2, and we have this result here. On the other hand, the angle OB prime C is what? Look at this. What is it? It's the exterior angle with respect to what triangle? B prime, A prime, C prime. And that means, by the corresponding theorem, the magnitude of this angle is equal to the sum of the opposite angles, gamma plus x. We do not know what this angle is. Gamma plus x. But these two angles, remember, they have the same magnitude due to the wonderful gift courtesy of the theorem 22. So that means that these two expressions must be equal one another. Gamma plus x is equal to gamma plus pi over 2, gamma plus pi over 2. Game over. Cancel gamma, x is equal to pi over 2. And that means that the set of points that make up the orbit of the images of the point C must be such that the points B prime and A prime, the fixed points, the line segment, must be seen from the image of the point C under what? Under a right angle. And what is that set of points called? Exactly, this set of points is called a circle that has the line segment B prime, A prime as its diameter, and that orbit is shown in red with the name Q prime that is associated. And look at this, precisely because this pre-image circle Q does not contain the center of inversion, our image circle Q prime, shown in red, Q prime, also does not contain the center of inversion. And that is the entire proof. It's not very complicated. It's almost verbatim lifted from the template that we used for the proof of for generating proofs of the theorems 15 through 19. And those of our viewers who are paying attention, they see right away that in this case we proved that the magnitude of the angle x over here was right. The magnitude was pi over 2 or 90 degrees. And the magnitude of the corresponding angle here at the vertex C was by construction right. But we can go in the opposite direction. We can take it that this angle over here, this circle Q prime, is very well can be pre-image. And what will be its image? Its image will be the green circle, but here we take that the magnitude of this angle is known to us. It's 90 degrees. And then through similar manipulations with the corresponding angles, we prove that the angle at the vertex C must be right. And now that we understand how a proof of the theorem 23 is put together, we can also construct an algorithm that uses the Euclidean tools alone, that will allow us to construct the image of a given circle that does not pass through the center of inversion, but has precisely two distinct points in common with the circle of inversion, using nothing but a compass and a straight edge. An algorithm for the Euclidean tools only construction of the image of the given circle Q, for example, that does not pass through the center of inversion and has precisely two distinct points in common with the circle of inversion, is very straightforward. If we understood a proof that we presented in the previous segment, then we should be able to put this algorithm together. It's shown on the bottom over here. First, step number 1, we construct the straight line, lowercase p of centers, or basically we snap a line through the center of inversion and the center, uppercase Q, of the given circle, pre-image circle. That much we can do. It can be done with the straight edge alone. In some sense, that tool was born for that task. Now, in this case, that straight line of centers P will intersect the given circle Q at two distinct points, out of which we actually need one. We do not need two. One point is enough. Let's say we take the point A. And as a step number 2, we reflect the point A into the point A prime with positive power. We have that point. We know how to do it with Euclidean tools alone. This was the subject of the previous problems, and that is why we solved these problems prior. Step number 3, now that we have the point A prime on the books and we know the location of the point A, what do? We bisect either the line segment A prime F1, A prime F1. Why is that? Well, we know that our target circle, the image, must pass through this point. Or likewise, we can bisect the line segment A prime F2. It doesn't really matter. Here, to avoid the clutter, I showed the line segment A prime F2 bisected with the perpendicular bisector named B. You can write more symbols over here that B intersects the straight line, the line segment, for example, A prime F, and that line, that perpendicular bisector B will intersect the straight line of centers P at the point Q prime, and this is precisely the center of the image circle uppercase Q prime sought after. This is the final step. Step number 4, we draw the circle lowercase q prime that has the point Q prime thus constructed as the center, and then the radius of this circle could be any one, for example, Q prime F2, Q prime F1 here, or Q prime A prime. It doesn't matter. Pick any such distance and it will work. Now, for a proof that this construction is correct, it is interesting to observe the following phenomenon. Let's say we take one point A and we call it pre-image, and we reflect it with the given parameters into the point A prime. Only then we bring in the side observer into the room and we ask the side observer, please present an algorithm according to which it can be deduced with absolute certainty and correctly which one of these 2 points is the pre-image and the other one, which one is the image. Yes, for demonstration purposes, I usually take the pre-image point designated with just a letter and I prime the designation of the image, but this is just an arbitrary convention. I can call one point P and the other one Q. So here is the point. It is impossible. The claim here is that there does not exist an algorithm that can distinguish, in this case, which point is the pre-image and which point is the image. All the side observer can do is walk up to our construction, measure the corresponding distances, construct the relevant product, witness the fact that that product is equal to the square of the radius of inversion. That much we can do with absolute certainty, and then we witness the fact that, let's say, the points that we have in question are collinear with the center of inversion and they are located on the same side. Here we can deduce with absolute certainty that the power of inversion is positive, but we cannot tell which point was pre-image and which point was the image. That information is not recoverable. It is that particular transformation is lossy in that way. And the whole idea of all these philosophical observations is that it is possible to apply exactly the same reasoning to our circle Q prime shown in red, as if it were the pre-image circle. And once we unwind all the steps that we did in the proof of the previous theorem, we take these points that we obtained by intersecting the straight line of centers through the Q prime and the center of inversion, reflect them with the needed power, obtain the other points, construct all the triangles, angles, theorem 22. We will actually, amazingly enough, come up exactly to the same equations, except that the difference will be here. When we reason in terms of the circle Q prime being pre-image, here that angle will already be known to us. We will take it as pi over 2 or as a right angle because that circle is given to us, and any circumference angle that subtends the semicircle is right. So this angle over here then will be designated with x. We will not know what it is, but through changing things around over here a little bit, so this angle will be x, this will be pi over 2. It doesn't really matter. After we cancel things out, the same angle gamma, boom, we will prove that the angle here under which the line segment AB is seen from the image point now C of the pre-image point C prime must be right, and the possible orbit or the locus of all these points must precisely be what? A circle that has the points A and B as its diameter. And that completes the proof that our Euclidean tools only algorithm for constructing the image of the given circle is correct, and we can finally move on to the final and the third corollary of the theorem number 22, and we will use the theorem number 23, the material in this theorem, also as the fodder to this corollary. As a final observation of this lecture, if we combine the results of the theorem number 22 and the theorem number 23, then we will observe the following neat result. If two circles, for example, the circle Q, shown here in green, and the circle Q prime, shown over here in red, two circles of distinct radii intersect at two distinct points like this, and these two circles are the inversive images of each other, for now with positive power with respect to the inversion of the corresponding plane in a given circle named C, with O as its center and R as its radius, then the center of inversion with respect to which these two circles are the inversive images of each other doubles up as a center of homothety of the corresponding plane, and with respect to that center, these two circles will also be the homothetical images of each other. And remember that homothety is the uniform expansion or contraction of the plane. So in a few seconds we will prove that, for example, if we fix our smallest circle Q, shown in green, and then uniformly expand the plane with respect to the center of homothety O, then this circle will be taken into the circle Q prime, and conversely, if we fix the circle Q prime as a given circle and then uniformly contract the parent plane with respect to the center of inversion, then we will zoom in this red circle into the green circle Q exactly, and here the point O, the center of inversion, again doubles up as a center of homothety of this plane and of these two circles. So how can we prove that? Well, again, we go back to our theorem number 22, the theorem number 23 that we just proved, and here we do one more thing. Remember that our straight line on which the original sample runner point C chosen on the given circle Q at random and its image C prime sit, that straight line will evidently intersect the green circle for the second time at the point D and the red circle at the point D prime. But this time it so happened that the point D is located outside of the circle of inversion, the white partially shown circle here, C. Consequently, with under positive power, it will be thrown inside of the circle of inversion on the same side. This will be the points D prime. D prime is the image of the point D with positive power inversion in the same circle. So here we again throw at all this beautiful mess our theorem 22 and apply it to the points A and C as we did in the proof, but this time we'll look at the interior angle at the vertex A. By that theorem 22, the magnitude of the angle OAC must be the same as the magnitude of the angle OC prime A. OC prime A. One more time, remember, if we have the angles, the order of the names of the vertices which form a given angle as OAC, we take the images of these points A prime, C prime, and then we swap them. So AC becomes C prime, A prime, C prime, A prime. So this angle I designated here with alpha. This is angle alpha, and this is angle alpha, and by the theorem 22 precisely because the points A and C satisfy all three conditions. They're distinct. Neither of them is the center of inversion, no point at infinity. They're not collinear and so on. This result holds. Now we do essentially what we now basically observe the following. The angle that sits on the other side of the angle alpha is what? Is the angle that completes the straight angle, because the angle A prime being the angle in the straight line is straight, pi radians. So this angle over here, which I designated as beta, is basically pi minus this angle alpha. This is captured over here. The magnitude of the angle CA prime, CA prime, this angle CA prime, this little leftover beta is what? Well, it is pi minus this angle alpha. But we have the same angle alpha here hiding over here. Now, let's say we will name our quadrilateral A prime, C prime, D prime, and B prime. By construction, based on the theorem 23, we see that this quadrilateral must be cyclic. In other words, the points of interest A prime, C prime, D prime, and B prime all sit on one and the same circle, Q prime. And what does that mean? That means that the sum of the opposite angles, or the sum of the angles of the opposite angles, the sum of the magnitudes of the opposite angles in this quadrilateral must be what? Must be pi. That means that the magnitude of the angle D prime, B prime, A prime must be what? Must be the magnitude of the corresponding angle over here at the point C prime, pi minus that angle, pi minus alpha. Pi minus alpha, because the magnitudes of these two angles at B prime and at C prime must sum to pi. Consequently, the magnitude of this angle is pi minus alpha. But now we have two equal expressions, pi minus alpha, pi minus alpha. That means that these angles over here, the magnitude of the angle CA prime and D prime, B prime, A prime, these two angles by magnitude must be the same. And what does that mean? That means that the straight line that passes through the points A and C and a straight line that passes through the points B prime, D prime, these two straight lines must be parallel. They must be parallel. And we know that the corresponding circumference angles at C and at D prime, they subtend a diameter of the corresponding circles. These angles must be right. And that means that the remaining angles that I did not show, but let's say I'll show them in orange, like so, must be the same as well. I will not give them names, but you understand what is going on. And what does that mean? That means that due to how these triangles are positioned in our diagram, that basically means that the straight line that passes through the points C and B is parallel to the straight line that passes through the points D prime and A prime. Parallel, 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 parallel. Now, that means that not only our right triangles A, C, B, and B prime, D prime, and A prime are similar, that is all fine and dandy, but due to how they are oriented in the ambient plane, these triangles are also the homothetical images of each other, precisely because the vertices A, B prime, B, and A prime sit on one straight line, the straight line of centers, and the remaining two vertices, C and D prime, sit precisely on one and the same straight line as well. So all the vertices of these two triangles are positioned in such a way that these two triangles are precisely the homothetical images of each other, and that proves our claim. In this case, these two triangles are the homothetical images of each other with respect to the center of homothency over here, this one, O. And we can compute it is possible to compute the coefficient of homothency. For example, we divide the distance OD prime by the distance OC, and in this case, this coefficient comes out greater than 1, for example, and that means that we, in some sense, took the triangle ACB as it, and then we uniformly expanded the plane into the triangle B prime, D prime, A prime, and that proves our claim. And in some sense, perhaps from a somewhat philosophical standpoint, that means what? That means that if we step away from our pointwise definition of inversion of the plane in a circle and look at how this inversion or how this geometric transformation acts on the given shapes as a whole, then in this particular case, the inversion of the real plane with respect to a circle is actually indistinguishable from the geometric transformation to which we refer as the homothency of the plane with respect to a certain point. In other words, the byproduct of both of these transformations is one the same: uniform expansion or a uniform contraction of the plane. But this is only in some philosophical sense. Of course, once we go back to the pointwise definitions of these transformations, of course, are different. This is it for the episode number 6, lecture number 6. And in the next episode, episode 7, lecture 7, we will keep looking at how the inversion of the real plane with respect to a circle acts on similar circles that do not pass through the center of inversion. But when we move our sample circle further and further away from the center of inversion, and we will play with different powers. In this lecture, we studied the inversion with positive power, and in the next lecture, we will look at inversions with negative power.